Okay, moving on. We're just going to talk in a little bit more detail about Newton's second and third law. Okay, so third law pairs. When objects A and B interact, the force of the interaction exerts on A is equal in magnitude and opposite in direction to the force it exerts on B. That's Newton's third law. Okay, but people get confused a lot. So let's say, for example, here I am standing on the ground, right? And I'm interacting with the earth, I'm interacting with the ground. So I feel a force due to gravity downward, and I feel an equal and opposite force due to the contact interaction, right? So a normal force. So they're equal in magnitude and opposite in direction. It sounds a lot like a third law pair. But is it really? And the answer is no. So third law pairs, here's how you can identify them. Each force in the pair must act on a different object, which is not the case here, right? Because both of these forces are acting on me. And each must reflect the same interaction. So if we look at this, force of gravity, what is a third law pair? It's saying that I am interacting with the earth. The earth is pulling down on me, and I am pulling up on the earth. That's the third law pair. It arises from the same interaction, and it's equal and opposite. I'm interacting with the ground, right? I am pushing down on the ground is pushing up on me. That's the third law pair. Same interaction, same contact interaction here. Okay, but we do, as I just was saying before, if you have some person standing on the ground, you have the force of gravity and a normal force, and those are going to be equal and opposite. These are equal and opposite due to Newton's second law, right? The second law says F equals ma. The net external force equals mass times acceleration. So these two are equal because I am not, or whoever this person is not accelerating in this direction. This is 0, the net force is 0, therefore the upward force and the downward force are canceling each other. So force pairs connected by Newton's second law act on the same object. That's true in this case. Arise from different interactions. That's true also. This gravitational force is arising from the gravitational interaction between the person and the earth. This normal force is arising from the interaction between the person and the floor. Act along the same axis. Check. And are equal because the acceleration along that axis is 0. Check. So example, normal force and weight, which we just looked at. But what if the object is suddenly accelerating? Let's say instead that my person is in an elevator that's accelerating upward. Try it out. We have some force scale kind of things that you guys could take in an elevator and try it. And think about how, so the normal force is kind of relates to our sensation of how much we weigh. So think about, as the elevator is moving up, do you feel heavier or lighter? Right? So the force of gravity is going to be the same. But in this case, when we move upward, the normal force is going to be greater. Okay? Because if the elevator is accelerating, we know the net external force is not equal to 0. So these cannot cancel each other out. It's a fun experiment. Let's make it extra credit. Try this at home. Or in Roger Bacon. Okay, so coupling forces. So whenever you have two objects that are interacting, right, Newton's third law says that the force that A exerts on B is equal and opposite to the force B exerts on A. So here, compare the forces exerted by the blocks on each other as they move on a table with some friction. Draw a free body diagram for each block. Determine if Block A exerts a greater force. Block B exerts a greater force. The forces are equal. All right. Free body diagram. Let's see how this is going to look. So here's block B. We have the force of gravity. We have a normal force. It could be equal and opposite to gravity. It says that there is some friction. So there's going to be some friction here, resisting motion. And then it feels a force, a push from block A. And the velocity is constant, so our acceleration is 0. So we know that the net force on this block has got to be 0. So that means the force it feels from A, it's got to be equal and opposite, even though it doesn't quite look like it, to the force of friction. Alright, how about block A? So it too feels the force of gravity, and it feels equal and opposite normal force. It's experiencing friction as well. And it is feeling a push. Okay, but it also feels a push backward in the same direction as friction from B. So that means actually my push here has got to be bigger. It's got to be the sum of those two. It's got to look like that. And that's what A would feel. Compare the forces exerted by the blocks on each other as they move on a table with some friction. Draw free body diagrams for each block. Determine if block A exerts a greater force, block B exerts a greater force. The forces are equal. So again, I'm going to tell you the forces are equal. Let's see why. Alright, force of gravity, force of the normal. Oops, I did it too long. Okay, and we know this is accelerating. So block B again is feeling some force of friction backward, which means that the force it's feeling from A has got to be a little bit longer. Okay, and then block A also feels force of gravity. It feels force of the normal. It too feels frictional force resisting its motion. A is pushing that way. On B, B is pushing equal and opposite force. On A. Okay, but it is accelerating. Right, so there's one more force we haven't taken into account, which is what this hand is doing. It's pushing on A right here, and it's making it accelerate. So it's got to overcome both friction and the force from B. So it's got to be longer than both of those. And that's the force of the push. Okay, so we're on to group problems, and there's also activities that we're doing in class, which will be third law. Activity. And that you're going to actually use 2 force probes, right, with a hook and another force probe, and they're going to be hooked together, and someone's going to pull this way and someone's going to pull that way, and you're going to be reading that out while you're pulling and pushing and seeing how those 2 forces compare. Right, so you can push as well. And then we want you to try this too, where you have 2 force probes hooked together, and someone's holding on here. Okay, it's a hand, it's supposed to be. And someone else is going to give it a big yank so that the force probes and the person attached to it accelerate.